What is this?
Circuit.
Okay, with
Battery.
and
Capacitor.
yep. For the purists, what is this?
Battery.
Not for the purists.
One cell battery.
What'd you say?
So 1 cell battery.
Generally not called a battery still at that point.
Power cell.
Yeah, power cell.
Is this chapter 27?
Yes, this is chapter 27. That's the one I wanted to grab anyway.
But the test is only from 23 to 26.
Correct. So the capacitor stuff, I'm trying to remember the chapter, what chapter 26 did. I mean, if you think of it as two evident planes, then that is fair game. Officially, the capacitors don't show up until chapter 27. But I think the parts that I had in the master set with the capacitor were fair game because it dealt with sort of the potential side. All right, but this stuff right here that we're about to do is very clearly 27. So we got a couple of equations that we're working with here. I know that capacitance is equal to the charge over the voltage. Capacitance is a positive value, so however you want to do it, these two are usually just use the positive for both of these. I know that for a parallel plate capacitor, capacitance is kappa epsilon sub naught A over D. Like in the lab, that is, I guess, due Saturday. I know that the electric field from the plates themselves is equal to sigma over epsilon naught. I guess that's the magnitude of the electric field. I know that the total electric field dot delta x, let's throw the minus sign in there, is equal to the change in potential. If there's nothing in between, the total electric field and the electric field from the plates is the same thing. Oh boy, and sigma is charge divided by area. And I feel like I'm missing an equation there. What am I missing? Well, it'll come up. All right, so let's start out with a 12-volt battery here. Plates will make 10 meters by 10 meters. The distance between them will make 1 centimeter. And let's start out with nothing in between. All right, so what's the magnitude of the electric field between the two plates?
Sigma over epsilon. Sigma over epsilon sub naught.
And what's, you said sigma over epsilon sub naught? Yeah, but we don't know what sigma is.
So is it Q
Oh, yeah.
over A over epsilon?
We don't know what
That's
Q
the
is.
other, oh. Oh yeah, it's the other equation.
The VED or Vex equation. So I know it's going to be my potential difference. Well, what is the potential difference between my two plates?
-12.
Depends on which way we're going, okay? It's -12 going from which plate to which plate?
From the positive to the negative? No.
Like you mean it.
From the positive to the negative.
Yeah, there we go. This is a higher potential than this is. When I'm looking at my battery here, the longer side is the positive side, the shorter side is the negative side. The positive side, this is higher potential. V high, V low. Those are relative terms. I have no idea what the actual potential is at either plate. All I know is the difference between them. So if I'm going this direction, then my change in potential is -12 volts. Suppose I stuck a dielectric in between. What's my voltage between the two plates? Going from positive to negative. If I stuck a dielectric in between.
Is it the same?
It is indeed. Why? Jesse, that was you, wasn't it? Okay. Just felt right.
I remember watching the lecture, but I forgot to read it.
Why is it the same answer?
Because it's V final minus V initial.
Yeah, but I can do other things to this, so that wouldn't be the same. Jesse, they're leaving you out to hang. What's going on here? Help him out.
Because of Kershaw's
Here, Puff.
yeah, and then just this law, that states that total is
Almost there.
total current in equals total current out.
Yeah, wrong one, the other one.
Well,
Would it be around a closed path, you end up where you started? Delta V equals 0.
Yeah, all right. So if we start here and go across the battery, we have gained potential. How much potential did we gain going across the battery?
12.
Yeah, 12 volts. Units are our friends. We gain 12 volts going across the battery in this direction, and then we cruise around and we get back to where we started. If I gain 12 here and I have to end up at 0, I better be losing 12 there. Or the short and quick answer is, as long as the capacitor is hooked to a battery, the voltage across the capacitor is fixed. If I want to change the voltage across the capacitor, I either need to change the battery or I need to disconnect it from the battery. And when I say disconnect, this is a nice board example of disconnecting. I'll talk about that in a moment. All right, so I got a 12 volt difference here, negative voltage if I'm going from high to low, positive if I'm going from low to high. All right, so I know what the voltage is. I have this equation right here, but really my potential is the negative integral of E dot dx dr, whatever letter we happen to be using at the time. When is this equation valid?
The electric field is constant.
Yes. And in this particular case, can we assume that it is constant enough? Given the information that I have for this particular problem, why can we assume our electric field is constant?
Because it's between two plates.
Not sufficient. That's part of it, but you missed a key point.
Is it the distance between the plates?
What about it?
Small.
Short. Small.
Keep going. What do you mean small?
Well, it's less than.
Is it, cause the distance is small enough to where the plates can be viewed as infinite?
Oh, okay, yeah, I guess that's not the exact wording I wanted. Kyle, did you say something?
It's 10% of
Hmm.
the total size of the area, right?
Or the dimensions?
Yeah.
Yeah, it's small in comparison to the plate size. That's why we can assume that they're infinite plates. Not drawn to scale. Recognize a centimeter is about like that.
Is that a rule, so like 10% of the area?
That, in general, yeah. If you're designing some piece of equipment where life and death is involved, I wouldn't use that rule.
It's good enough.
Yeah, yeah, I mean, it's good enough for what we're doing here. I accept no responsibility for any deaths caused by these students in making that assumption. All right, so, yeah, so electric field's constant, we're assuming it because the distance between it is small using the 10% rule. It is indeed close enough. All right, so this would be my, so this is basically my potential divided by the distance between them. So we had 12 volts over 0.01 meters, or 1200 volts per meter, or 1200 newtons per coulomb, whichever one you like. All right, so I now know what the electric field is. What's the surface charge density? All right, so your textbook uses sigma or eta. I hope you use sigma because that's what I've been using. But I think the flashcards use eta because I based it on the previous book.
I think it uses sigma.
Sigma, okay, we'll continue that. All right, so how do we find the surface charge density?
Magnitude of the electric field times epsilon sum.
Yep, using this equation over here. So we have 1200 newtons per coulomb times epsilon. And what's epsilon without looking it up?
8.85 times 10 to the negative 12.
Coulomb squared over Newton meter squared.
All right. And just to make sure that the units work out right, I mean, typically, yeah, you're multiplying, you're staying SI units, you're gonna be good, you should know what the Q is gonna be in the end. But that Newton cancels out with that Coulomb cancels out with that, and we'll end up with coulombs per square meter, which is surface charge density units. And we get
1.08 times 10 to the 13 coulombs per meter.
times 10 to the,
13.
Yeah.
That's not what I got.
I got 1.062, the third times 10 to the -8.
That's
Oh,
what I got.
wait, I did times K.
yeah, that would make a difference. 0.62
Yeah.
newtons per square meter. Nope, coulombs per square meter. And now, what is the charge?
Sigma times the area.
So this times 100 square meters. So 1.0 1.062 times 10 to the negative sixth coulombs, or 1.062 microcoulombs. For those fans of prefixes. All right, so I know the charge and I know the voltage, so let's find capacitance two different ways. Let's take this one right here, and the capacitance is our charge. So 1.062 times 10 to the negative sixth coulombs divided by my voltage, which is 12 volts. Oh, 8.85 times 10 to the negative seventh.
Negative 8.
Farads. And using the other formula here, what's kappa in this particular situation? What is the dielectric constant?
1.
Close enough. Yep. If there's nothing in between them, it is indeed 1. If there's air in between it, it's 1.00006 or something close enough. All right, so this is 8.85 times 10 to the negative 12 times my area, which is 100 square meters, divided by the distance between them, 0.01, and you get, well, that same thing. Questions on this, because we're about to change something. Sort of recap what we have here. So we start out initially. We have electric field total is equal to the electric field plates from the plates, which was 1200 newtons per coulomb. We have the voltage between it, at least absolute value of it is 12 volts, positive or negative, depending on which way you're going. We had sigma is equal to 1.062 times 10 to the negative 8th coulombs per square meter. The charge, 1.062 times 10 to the negative 6th coulombs. And capacitance, 8.85 times 10 to the negative 8 farads. I think that's all the information we calculated over there. Now, I want to cut the potential in half without making it a 6-volt battery. How can I change the potential difference between the plates?
When you double the distance.
If I double the distance here, that would indeed affect D here, which would make capacitance twice as big. However, it would also let's see, what else would that affect? If we double the distance, we cut our electric field in half, which means we're changing our charge. So charge gets cut in half. Wait, if we double the distance, that gets cut in half.
That would have to get cut in half.
So that would be cut in half. Based upon this, the electric field would be cut in half, which means that the charge is cut in half. And if the voltage is cut in half and the charge is cut in half, then the capacitance, yeah, there's an issue there. The voltage actually does not get cut in half. You have to do something else first. Why is just adjusting the distance right now not going to help us cut the voltage in half? Last time it took Jesse, Kyle, and Austin to answer this question.
Because it's in series.
Because it's what?
Because it's in series with the battery.
Yeah. The battery sets it. It's gonna be 12 volts. No matter what we do here, this battery is set to 12 volts. So what do we have to do in order to release it from the domination by the battery?
You have to put in a dielectric.
Putting in a dielectric, still gonna be 12 volts in between them because. Disconnect, yes. Now, in reality, I have two charge plates here hooked to a battery. They are indeed charged. If I disconnect it, what is actually going to happen, physically, if I do this in the classroom, what is physically going to happen is that I cannot disconnect it fast enough, and so once the connection is just slightly off, it's going to spark. So in reality, you need to be able to disconnect it as fast as you can, as fast as, actually faster than any of one can physically do it. There are machines which can disconnect it quickly, but physically, if I'm doing it by hand, I cannot do it fast enough. I will refer to this as an ideal disconnection, that we can disconnect it fast enough, somehow, mysteriously, even though we will not reproduce this in the lab, but we will assume that I can disconnect it so quickly that there's no loss of charge. Once I've disconnected it, my charge is now fixed. So while it's hooked to the battery, voltage is fixed. When I disconnect it, charge is fixed. That'll come in handy later. Probably on test 1B.
So charges are fixed when it's hooked to the battery? Charges are fixed when it's hooked to the battery?
No, charge is not fixed, because if you change the size, the amount of charge on the plates will change. So now we have fixed our charge. So if we disconnect, my charge is 1.062 times 10 to the negative 6 coulombs. Now let's see what effect happens. Let's go with Mario's suggestion of just doubling the distance. So charge stays the same, therefore sigma should stay the same, because it's charge divided by area. So this is 1.062 times 10 to the negative 8 coulombs per square meter. Since my electric field is sigma over epsilon sub naught, my electric field should stay the same. 1200 newtons per coulomb. Since voltage is my electric field times the distance between them, if I double the distance, what happens to my voltage? Yeah. But if we want to cut it in half, what do we do to the distance?
Half.
Yeah. So if we change D to 0.005 meters, so bring them closer together, now my voltage is half of what it was. Now it's 6 volts. My capacitance, I have the same amount of charge, but I have half the voltage, so my capacitance actually doubles. So it's now 24 Sorry, wrong one. 17.7, times 10 to the -8 farads. Or from this equation right here, if D is cut in half, then the capacitance should double, which is what if I did the math correctly, what happens here. So on test 1B, and I know your mind's not necessarily there yet, but you might want to just make a note. There's going to be some question about, I give you a setup, and then I ask you, what do you do in order to create, double this, but keep that the same, that kind of thing.
So, I'm kinda confused on algebra.
Yep.
So, when you break the circuit, why isn't everything zero? Is there still power in the capacitor?
There's still charge on the capacitor. We assume that the capacitor is still charged, so if I touched it, I get
Oh,
zapped.
okay.
Yeah, it has to be hooked to the battery first in order to charge it, and then we do this ideal disconnection so the charge stays there.
Okay.
So if it wasn't an ideal disconnect, just because I was wondering, what is the spark? Is the loss?
What is the spark?
Yeah.
Um,
You said it was spark. If we went-
Yeah, because there's charges on the plate, so as I'm disconnecting it, it may be like shuffling your feet across the floor and then touching the car or the doorknob. It's, you have enough charge built up that it wants to escape. So that's what would happen.
So all the charge will be gone?
Would I try this? Yes, close enough. In reality, probably not all, but,
Most of it.
from a physics point of view, where life and death is not at stake, yeah, we can say close enough to all. All right. Parallel plate capacitors. You've done a lab on them. We talked about sort of the background behind it. Let's look at two other different types of shapes. The cylindrical and the spherical. And I guess I wrote the note down of, well, I have equivalent capacitance. Oh, yeah, there was one other thing I wanted to do before I got to those. Another follow-up. What is the equivalent capacitance of these two capacitors in series? Or how would you find it?
You would add them, correct?
Not add them like this.
It's, the 1 over.
Yeah. So 1 over the equivalent capacitance is 1 over 3 plus 1 over 2, which is 5 over 6. And so my equivalent capacitance, 6/5, 1 farads. For those who've had some physics before, and I know that about half of the class usually has had this kind of stuff before. Resistors are the opposite. Resistors in series you just add straight up, and resistors in parallel you would do the 1 over bit.
So why would we do 1 over?
But why is this 1 over?
Yeah, 'cause that made sense to just like add a 3F plus 2F.
Because if I have this thing hooked to a battery and I've got a capacitor here and a capacitor here, charge is gonna, as soon as I make the connection, the electrons are gonna leave the negative side and they'll show up on this plate. As soon as it shows up on that plate, it chases an electron off of this side, which shows up over here. It chases an an electron off that side, which then eventually makes its way to the battery. In reality, the time it takes for an electron to get from here to here is, you could use a stopwatch for that, using just normal, if this were, represented the actual size. What shows up here is an electron pops up there, leaving a hole which is filled by an electron, and then there's just basically this chain of electrons that move. All right, so I know from Kirchhoff's rule that whatever voltage I gain here, I'm gonna lose some here, I'm gonna lose some there. So the potential across the battery plus the potential across, we'll call this 1 and 2. 1 plus the potential across 2 is equal to 0, because Kirchhoff says so. So, because I'm going that direction, it's going to be a loss. I know that capacitance is equal to Q over delta V. And so delta V is equal to Q over C. So this would be, we have some gain across the battery minus Q over C1 minus Q over C2 is equal to 0. We're looking for an equivalent capacitance, and basically, I have some charge here, negative charge here, I have the positive charge here, negative charge, positive charge. It's not like I've stored additional charge here. So this right here would just be Q over the equivalent capacitance, which would be equal to Q over C1 plus Q over C2, and then that's the essence of it. It'd be like I took this capacitor here and just stuck something in between. Did that answer your question? Okay. And then 3 farads. I'm heading to someplace different than what we did on the other day. 2 farads. And the equivalent capacitance is? And the analogy is if I have a 5 farad capacitor here and I just basically split it into 2 of them. So that. Now, here's where I was heading with this.